Hello, students. Today we're going to tackle a very important topic in coordination chemistry, and that is the stability of coordination compounds. But before we jump into all the theory, let me start with a question. Just imagine, how is it possible that a single chemical can actually save a person's life from something as dangerous as heavy metal poisoning, like from lead? Well, the answer to that life-saving question lies right here in understanding the stability of coordination compounds. This one idea is what helps us predict which chemical bonds will last and which ones are going to break apart. Okay, so let's get into the heart of it. What do we really mean when we use this word stable in chemistry? It's a common word, but it has a very specific meaning for us. At the most basic level, you can think of stability as being all about the strength of a grip. You have a central metal atom, and it's folding onto its ligands. The question is that grip strong and firm, or is it weak and loose? That's really the core idea of stability. So, a stable complex, you see, has a very strong grip. It holds its ligands tightly and it resists any change. On the other hand, an unstable complex has a weak grip. Its ligands can just fall off or be replaced very easily. It is this grip strength that decides if a complex is going to last in a solution or just fall apart. Now, to really make this idea clear in your mind, let's build a simple mental model together. This will really help you visualize what's happening at the molecular level. This analogy is actually very, very helpful. Think of a stable complex as being like a really strong magnet. It holds on to little metal pieces so tightly that even if you shake it around, they just don't fall off. Now, an unstable complex, that's like a weak magnet. The slightest disturbance and the metal pieces just drop away. All right, let's build on this a little more. Picture this in your mind. You have a central metal ion. This is our anchor, right at the center of the complex. Now, if this complex is unstable, imagine that the ligands are attached to that central metal ion by very thin, very delicate threads. You can see how any small push or pull would just cause those threads to snap, and the ligand is lost. But in a stable complex, it's a completely different story. Here, the ligands are held to the metal ion by thick, strong ropes. These ropes are very, very hard to break. Other molecules can come and bump into the complex, but the ligands, they will hold on tightly. This picture really shows you the difference in bond strength. So a very natural question comes up now. We understand what stability is, but why are some complexes held by strong ropes and others by weak threads? What are the actual chemical reasons for this? And understanding these reasons is very powerful. It allows us chemists to predict which combinations of metals and ligands will form compounds that last a long time and which ones will be very temporary. One of the most important guiding principles here is something called the hard, soft, acid-base principle, or HSAB. Now, don't worry about the name, just think of it like a simple matching game. Hard acids, which are small metals with a high charge, they prefer to bond with hard bases, which are small ligands. When you get this match, you get a very stable complex. Similarly, soft acids, those are larger metals with a lower charge, they form very stable bonds with soft bases. But when you have a mismatch, say a hard acid with a soft base, the grip is much weaker and the complex is less stable. So to just quickly summarize, stability really depends on three key things. First, the nature of the metal ion itself, its size and its charge. Second, the nature of the ligand. And third, there is a special factor called the chelate effect. This is when ligands can grip the metal at multiple points, almost like a claw, and these form exceptionally stable complexes. All right, that is enough theory for now. Let's see how this concept actually works in the real world. How is stability really used to save lives, and what can we see with our own eyes in the lab? Remember the question I asked at the very beginning about lead poisoning? Well, here is how the treatment actually works. The toxic lead, it binds to important proteins in our body. This causes serious harm. So what doctors do is they introduce a special ligand, a chelating agent. This agent is designed specifically to form a much more stable complex with the lead. Because this new complex is more stable, the lead ion leaves the protein and it binds to the new agent instead. This new complex is harmless, and it's safely flushed out of the body. The whole treatment depends on this principle of forming a more stable compound. And you can actually see this difference in stability right in the lab. If you take a solution of the ferrocyanide ion, it has a deep yellow color that stays the same for months. This shows it is incredibly stable. But if you take a solution with the hexaaquaferrin ion 3 ion, It's a pale purple color. And if you add almost any other ligand to it, the water molecules are replaced instantly and the color changes. This tells us it is a very unstable or labile complex. And this difference is not just a small one. It is huge. The stability constant for the cyanide complex is more than 10 to the power of 39 times greater than that of the water complex. That is an unimaginably massive difference in stability. It just shows how strong some of these chemical grips can be. So, as we come to a close, let's just recap the most important takeaways. First and foremost, remember the core idea. Stability is simply a strong grip. Second, remember that mental picture? Visualize those thick, strong ropes holding the ligands tightly in a stable complex compared to the weak threads in an unstable one. And third, remember the real-world application. Think about how chelation therapy uses this very principle to save people's lives from heavy metal poisoning. So my advice to you is this. Just remember these three things: the core idea of a strong grip, the mental picture of strong ropes, and the real example of chelation therapy. I promise you, if you remember these, this topic will feel much, much lighter when you face it in your exam. And that leaves us with a final thought to ponder. Now that you understand this powerful principle of stability, what other life-saving molecules could we possibly design just by carefully controlling that grip between a metal and its ligands? Thank you.